Welcome to SCP 140, our exploration of problem set number 2 for topics in astronomy. This problem set deals with chapters 3, 5, and 6, mostly having to do with gravity, light, and telescopes. As you log in, we're going to head on over to week 4 assignments and check out the second problem set, gravity and light. There are a number of problems here, most of which have to do with the phenomena related to gravity and light. Please do read through the instructions, make sure how they understand the way all of this works, but it is very similar to the first problem set. Our first question deals with phases of the moon. If you understood our phases of the moon lab, hopefully you should be able to answer this question. I will give you one hint. This is the northern hemisphere moons. So you should be careful when you look at these images that you compare them to what they should look like in the northern hemisphere compared to the southern hemisphere. There is a difference in the orientation of first and third quarter moons. Question number 2 asks you to deal a little bit more with the size of numbers. We call them order of magnitudes, logarithmic counting, exponents, powers of 10. We're going to be looking at, in particular, ways of thinking how these big numbers propagate when we do different sorts of measurements. For example, we have been trying to look at things like the distances between 2 points. And maybe we give a measurement for the distance between these 2 points. I'll take 10 to the, let me give a big number here, 10 to the 10. And perhaps we'll even use kilometers as a distance. So imagine that I had something that was 10 to the 10 kilometers away. That's about 10 billion kilometers. That's almost well out past the orbit of Saturn, well out past the orbit of Uranus. We're way out in the outer edge of the solar system at this point. So we're going to think about a distance that's long. Now, sometimes we'll have to do things like think about areas, 2 dimensions, especially when we try to think about phenomena that pass through space. Like maybe we'll think about light passing through space. Or maybe we'll think about a flow of material or fluids passing through space. In that case, we'd want to do areas. And every length has a characteristic area associated with it. And we can get that area by thinking about what would happen if we made a square where each side was approximately that length. So if I make a square where each side is approximately that length, then the question would be, how big would the square be? Right, so I've got one length that's the size of 10 to the minus 10, sorry, 10 to the positive 10, and another length that's the size of 10 to the positive 10. Now, if you remember what the formula for area is, it's length times width. In this case, our length and our width are the same. If we called them L, it would be L times L, which is the same thing as L squared. That would be the area of a square that had, in this case, a side that was 10 to the 10 kilometers. Well, I can do this by using some of the tricks I know for exponent rules. And we'll be using these tricks a lot in this class. So this is a nice way of getting familiar with how these tricks work. Let's say I have, oops, I miswrote this. Let me just change that exponent there. It should be 10 to the 10 kilometers. So we'll put a 10 here, 10 to the 10 kilometers. And what I'm going to do is I'm going to square that. Now, when you square a measurement like this, you square the numbers and you square the units. And this is something that students sometimes don't realize, that square is going to actually multiply everything on the inside by itself. And since we can reorganize multiplication any way we want, what we normally do is we square the number and then we square the units. Squaring a number like this, if it is only a number that's raised to a power means multiplying the exponent. So 10 to the 10 times 2 would be 10 to the 20. But it's not 10 to the 20 kilometers. That's a distance that's in a line. We call it a linear distance. This is 10 to the 20 square kilometers. Imagining a distance that's kilometer on one side and then another distance that's kilometer on the other, making a square, I would have 10 to the 20 of these things if I traced out the square I described above. And to write square kilometers is pretty simple. We usually write km and then a little 2 up at the top to indicate that it's square kilometers. There we go. One of the confusing things about square kilometers or square units in general is that that exponent 2 hits not just the measurement base unit, the meter, but it also hits the kilo. That kilo is actually squared. And a squared kilo, 10 to the 3, is the same thing as 10 to the 3 squared, or a million. Another way of saying this is that within a square kilometer, there are a million square meters, and a tremendously large amount of area. The areas kind of multiply faster, more exponentially growing than do lengths. If I make a length bigger, by a certain factor, the area is going to grow by the square of that factor. And that's an important thing to keep in mind. We can keep going and we can actually move into the third dimension. We move into a third dimension, I end up tracing out a cube. I'm going to try to do this as best as I can. So here's my cube that I'm tracing out. This is the traced out cube. Lots of busy things going on here. So if you can't quite understand what's going on, think of this as a three-dimensional cube now with an additional side here. So instead of now calculating the area, what I'm going to do is calculate the volume of a cube. That's the three-dimensional equivalent of a length. So volume is going to be length times length, and then I'm going to have yet another length here. Running out of space, so I'll just add it on to this side here. Instead of length squared, that becomes length cubed. And I can play the same game down here as well. 10 to the 10 kilometers, not squared any longer, but now it's going to be 10 to the 10 kilometers cubed, which instead of 10 to the 20 is going to give me a number like 10 to the 30. That's one with 30 zeros behind it. That's how many cubic kilometers there would be in this gigantic cube. And of course, if I'm going to do this abundantly correctly, what I want to make sure is I get the right units here. It's no longer kilometers squared. Now it is kilometers cubed. Same thing applies as before. Kilometers cubed, the meter is being cubed, but the kilo is also being cubed. Kilo cubed, 10 to the 3 cubed, that's a billion. There are a billion cubic meters. A cubic meter is a cube with a meter by a meter by a meter. It's about twice the volume of a human being, typical. If you would have a billion of those, that would create a cubic kilometer. So a square with a kilometer by kilometer by kilometer, you could create a cubic kilometer. That would be a billion of those cubic meters put together. So volumes multiplied much more quickly than even areas, and certainly lengths as well. This is the sort of work you're going to be doing here in this problem, thinking about different units, squaring, cubing, and then even comparing different units. There will be a division problem you have to do as well. Okay, so let's continue on. Question number 3 asks to do something similar that you did in question number 2. In this case, we're actually comparing two volumes. So the same thing is going to happen in this question. You're going to take the length scale of one object, the length scale of a second object, and find the volumes of the two of them. And then you're going to divide the large object by the small object. That's going to tell you how many small things you can fit inside the large thing. In this case, we're going to try to fit a certain number of atoms in the habitat of all Milky Way planets. In other words, the locations where people or life might be able to survive in planets all across the Milky Way. If you imagine that as a certain space, how many atoms could you fit in that space? That's what we're going to answer here. Question number 4 has you think a bit about light. Now, if you followed along with my exploration of gravity and light, you'll have some sense here. Different people will get different questions. And the key thing to know here is that you want to be able to calculate either the wavelength or the frequency of light using a very particular relationship. Wavelength and frequency are related to each other in this fashion. If I take the speed of light, that's equal to the wavelength, which we usually use this symbol, which is the symbol lambda, times the frequency. Wavelength times frequency is speed. And the speed of light is a number and measurement that you should become very familiar with over the course of this class. I'm going to use the speed of 3 times 10 to the 8 meters per second. You might see it listed in different ways in different places, but this is going to be useful for us. Now, I have a wavelength here. That wavelength is 4.25 times 10 to the minus 7 meters. If I take that speed of light and divide by the wavelength, I should be able to get the frequency. So here I'm going to put in that divided by 4.25 times 10 to the minus 7. And the units of wavelength are typically units of length. In this case, it's meters, but someone may have given you units of length in centimeters or even nanometers, even smaller units. But this equation should tell me the frequency. And I could use a scientific calculator to calculate this, but there's a few things I'd like to point out. One thing to point out is that when you do these calculations, take note of the units because some units will cancel. And in this case, the meters cancel, leaving me with a bizarre unit that looks like divided by seconds. Another name for this unit is hertz. This is the unit of frequency, how many waves come in a given second. Now, other things I'm going to do is I'm going to be dividing numbers by exponents, and I've had some students ask me questions about how to do this. 10 to the 8 divided by 10 to the minus 7. Some students erroneously sometimes write that this should be 10 to the minus 1, and that's not correct. It is indeed correct that you subtract the exponent that's in a denominator from an exponent that's in a numerator when you're doing the rules for exponents. But in this case, 8 is the number in the exponent in the numerator, and -7 is the number in the exponent in the denominator. And you can see that if I take 8 minus -7, I don't get 1 or -1. It's another number. And so you should take care and see exactly what's going on, making sure you keep track of negatives and positives. Just so that you're clear, you should get a pretty big number for the frequency. The frequency of light is up in hundreds of terahertz when you can see it with your eyes. Question number 5 basically asks you to do the same thing again, in this case with radio waves that have perhaps a given frequency or a given wavelength. And you're going to have to do the same thing that you did with question 6. In question 7, same thing again. You're going to be doing the same thing. You're doing these calculations for figuring out wavelengths and frequencies. Here are some more questions that may be involved with the chapter that you're reading. And now we have a pretty fun question which asks you to look at all the different forms of light. This includes light that you can see with your eyes and light that you can't see with your eyes. And below here, we've got these measurements of wavelengths and frequencies, and in some cases, energy. Light carries energy along with it in the form of photons, and the energy of a photon is directly related to its frequency. Now, to figure out the energy of different forms of light, you may have to go look these things up. They're in your textbook, but they're also easy to discover online, or if you're going to do some of the supplemental reading and research that we have linked on our webpage. So we have measurements of wavelength that are usually measurements of distance, kilometers, meters, nanometers, and so forth. We have measurements of frequency that are usually in the form of hertz, or sometimes a prefix in front of hertz, like kilo, mega, giga, terahertz, things like this. And then we also have measurements of distances in other units as well. For example, I see microns on here. Micron is the same thing as a micrometer, which is a millionth of a meter. Finally, when we measure energy, we're often going to give the energy in units of electron volts. This is a weird form of energy that comes from the discovery of certain particles, in particular electrons, and how fast they moved, how much energy they were given in an electric circuit or parts of an electric circuit. And in this electric circuit, you would have something called an electron that could gain energy by virtue of the voltage on the circuit. Voltage is a concept we're not going to worry about too much in this class, but there is an amount of energy, which is called 1 electron volt, which is approximately the amount of energy that's given to an electron if it passes through this, what we call potential distance. It's an electrical situation that gives energy to photons. And it gives energy to different particles. When we measure the energy of photons, we usually measure it in this unit, the electron volt. And you can see some of these things being measured here, energy of a single photon in electron volts. You're going to look at some of these and make decisions about where on the electromagnetic spectrum they lie. Some of these measurements you may find are a little ambiguous, and you'll want to make sure you understand completely. The reference is quite nice here, but it doesn't necessarily cover the edge cases as clearly as you might want. So you may need to do some additional research, either in the text or on your own. Question number 9 asks you to think about gravity. We are going to be thinking about, in particular, different worlds that have different gravity. And if you stand on one world that has a different gravity than our world, you're going to experience different weight. We usually measure weight using units of force, and the most common unit of force is the Newton. In this situation, my weight is changing because I'm moving to a different planet. On planet Earth, our acceleration due to gravity also causes weight. The fact that things fall towards the Earth is what gives us weight. Our acceleration due to gravity here on the Earth is about 9.8 meters per second squared. You can round that off to 10 meters per second squared in this class, and you'll get the right answers. We have a wide range of tolerance for different numerical answers. We want you to just estimate these numbers, not necessarily get them 100% accurate. But in this case, what we're thinking about is a situation where the weight is changed. Your weight is now a different weight. And if on Earth we experienced 9.8 meters per second squared of acceleration, what are we experiencing on this other planet if my weight has gone down? Surely we should be experiencing something less than that acceleration. Now, your job is to think about how much less and try to figure out which of these answers is correct. I'll give you a hint. It has to do with proportions. Now we're going to think a bit about how forces of gravity work. The force of gravity is related to how far away you are from the center of the gravity, and also how massive the thing that you're being pulled towards you is. And that force can be written down in a number of ways, and they definitely do this in your text. But the easiest way to consider the force is to say that it's proportional to, and I'm going to use this symbol to proportional to. In other words, as I do something to one side, the same thing happens to the other. It's proportional to the mass of an object divided by the distance to the object, but multiplying that distance squared, almost like it's an area we were doing before. So that means if I increase the mass by a certain amount, the force will increase by the same amount. But if I decrease the radius by a certain amount, the force will also increase, but it'll increase by the square of that factor that I change things. That's a key piece of information here, hopefully helping you answer this question. We have also talked a bit about how planets move around in our solar system. And there's one particular law that's described here. This is called the law of planetary motion, the third law from Kepler. what Kepler said was that in our solar system, if you take the period of an orbit of a planet and you square it, that's the same thing as the distance cubed. As long as you're measuring your periods of orbits in years, such as the period of the orbit of the Earth, and you're measuring the distance between the planet and the sun in this unit called the astronomical unit, which uses the distance between the Earth and the sun as 1. It's about 1.5 times 10 to the 8 kilometers as an astronomical unit, but you could just call that 1 astronomical unit and be safe here. That's the sort of unit we're using here. And in this problem, everybody's given a different asteroid that's some distance farther away from the sun than the Earth, let's say. And maybe you're given the period, or maybe you're given the distance, but either way, you can plug that number into this formula here. And if you plug it into this formula, you should get the result that you're looking for the thing that's unknown. Now, what's interesting about this problem is I've chosen particular measurements of periods and distances so that you could, if you were clever, be able to calculate this without using a calculator. All you would need would be this information down here, which is square and cube numbers that are perfect cubes and perfect squares. That's sort of a challenge for people wanting to do this problem without a calculator, but of course you can use a calculator if you'd like. And now for the rest of these problems, 12, 13, 14, 15, 16, 17, 18, 19, and 20, all the way through to problem 25. Most of these are going to be related to the chapters that you're reading. So you should make sure that you read chapters 3, 5, and 6 in order to answer these questions. Okay, so that's basically everything I wanted to show and share with you. I hope that this has been a useful walkthrough. We'll post this up, and you hopefully will be able to finish your problem set in due time. Thanks very much, and see you all later.